Welcome back, ladies and gentlemen. Here in this video we are talking about the equations of motion, specifically when acceleration is constant. And that's really important to remember. In this class we're not really going to be dealing with changing acceleration. Acceleration does change from time to time. It happens in real life all the time. But for what we're studying, we need to remember that our acceleration will be constant in the situations we're going to analyze. But you'll also hear this term, kinematics. Now, kinematics is basically the study of motion, how to describe the motion, how to analyze the motion, but not really getting at why the motion takes place or why the motion changes. It's just what is the motion taking place. Let's get going. We have to get to some equations. We're going to end up with what I refer to as the big five equations. We'll get there. Let's start by looking at definition for average acceleration. Recall that average acceleration is simply defined as change in velocity divided by the time interval that it takes to change that velocity. Break this down a little bit. And so a change in velocity is just a final velocity minus an initial velocity, right? And now time, the time interval. For some problems, once in a while, you're going to have a time interval where we don't start counting the time at t0 or at t equals 0. But for the most part, that's what's going to happen. So if t initial equals 0, then the time interval, the change in time, is simply equal to what the final time is. And so what I'll usually do is I will usually drop the delta symbol and just write time. And so looking at this, we can just call this, well, if acceleration is constant, then average acceleration is also equal to instantaneous acceleration. They're the same because acceleration is never changing here. All right, so rearranging this a little bit, and that's convenient so we can have a simpler symbol to use in the equations. But rearranging this, let's look at final velocity. And we'll say that rearranging this part, this is equal to initial velocity plus acceleration times time. Your textbook is, and some other sources are possibly going to look at this and say, well, you know, they drop the F, and they drop the I, and they use different symbols here. So you'll just see V equals V naught. And that means the initial velocity, the beginning velocity, same thing. When you just see this, it essentially means final velocity. More or less the same thing. So velocity at any moment in time, velocity at any given time. Well, you have to take into account any initial velocity that it had. You also have to take into account the rate of acceleration. But look at this. This sure looks like almost like a y equals mx plus b with you know, obviously things are kind of mixed up a little bit here and out of order, but that doesn't matter. And that's exactly what's going on. When you view this equation as a line on a graph, then the graph you're looking at essentially is a velocity time graph, and its slope is the rate of acceleration, and the initial velocity, whatever that is your y-intercept on that graph. And so we already have the very first equation of motion. Remember, velocity at any given time, initial velocity taken into account, and that's the y-intercept on a VT graph, and then your slope of the graph is your rate of acceleration. So your A is shown as the slope. Slope m equals your acceleration. So, first equation. Boom. There you go. Now, we're just getting started. So, instead of looking at average acceleration, recall the definition of average velocity, right? So what we saw was it's a change in position divided by, well, a time interval, and I'll drop the delta in front of the t. And so we're going to rearrange this up, and we're going to say, well, you know, a change in the position, that's going to be a final position minus an initial position. Divide that by the time. And now I can't say that it's equal to instantaneous velocity, that because velocity is changing. That's not the case here. However, we're going to rearrange this, and we get to see that final position is equal to initial position plus average velocity multiplied by time. The form you see is very similar to what we just saw, right? And now we're not done here though. I'm going to take a look at this, and so we can also say, well, there's another way to look at average velocity. Well, the average velocity, an average of two numbers, we have an initial velocity and a final velocity typically. And so an average of two numbers is adding those numbers up and dividing by 2. So we have 1/2 initial plus final. There's another way of looking at average velocity. And so a quick substitution, we're just kind of combine these two things. We get this, and also remember, because I'm trying to stay consistent for you, so I'm going to drop the F and the I, and we're going to go with this. So your position at any moment in time has to take into account your initial position, but also it is your average velocity multiplied by the time interval. Okay, so there's two things going on that you really want to be aware of. So the first is this guy right here, understanding this basic thing about average velocity, and this guy, where you can find the position of an object at any moment in time if you know its initial and final velocities and its starting location. So you have two more equations of motion here. So what do we have so far? We can find the velocity at any given time if we know the initial velocity and the rate of acceleration. We can find the average velocity if we know the initial and final velocities. That's kind of an obvious one maybe. And we can find the position at any given time if we know the initial position or the starting position and the initial and final velocities. All right. But there's more, of course there's more. That's only 3. So it gets interesting from here. Check this out. Now, mentioned graphical relationships where you had, something like this. If you sort of view this on a graph, you get this form y equals mx plus b, right? Well, there's more to it. We might say, you know what, if we have a velocity time graph and we have an object that is starting out at some initial velocity and is accelerating, so the velocity is changing like that, right? So we want to find how far this thing goes, or its displacement, or maybe its new position, however you want to think of it, after that time interval. But we would like to kind of develop an equation for that, and that equation can actually come from this graph. Hang on a second, that's bugging me. So what's going on? Well, if we multiply, you guys know this already, right? If we multiply a velocity times a time, well, you're basically going to get the change in position. We've seen that already. So what does that indicate for us, though? Look at this, multiplying velocity times time. If we take this axis, the information on this y-axis, which is velocity, multiplied by the information on this axis, which is time, we're essentially going to find the area under this graph. And so what's going on here? I mean, not using any calculus techniques, just let's check this out. Well, this is a bit of an odd shape, but it's easily broken up into very simple shapes for which the area would be easy to find. So what are the dimensions here? Well, we have a triangle, and we know the two sides of this triangle. Check this out. This side is basically just t from here to here. That's our time t. And how about this side of the triangle? Well, that is, see, here's our new velocity. And so this side is our change in velocity. And if you know the two sides of a triangle, you can find its area, 1/2 base times height. Easy. Now, how about this rectangle? Well, this side of the rectangle is, well, if we started at velocity of 0 there, its initial velocity is this value, and so That's the side of that triangle, or I'm sorry, rectangle. And then this long side is still t. So we can put this together and essentially say, you know what? The area under this graph, which we're saying is going to represent the displacement of the object, is easily found with those two simple components. So, here we go. Let's try this out. So we have this displacement, and we're going to say we have the area of the rectangle, and we're going to add to it the area of the triangle. And just running out of room, so I'm abbreviating. The area of the rectangle, well, that's going to be initial velocity times time. The area of the rectangle, we have 1/2 base times height, so 1/2 t times delta v. I'm going to write the delta v first. That's how it's more traditionally written, in this order. The order does not matter, obviously. There we go. And so this is displacement. Now. Check this out. Okay, I'm gonna expand that. BOT plus 1/2. Delta V is going to be final minus initial. Final minus initial. Okay, no big surprises, no substitutions. That was just an expansion of the delta V. And well, now this is cool. There's something else here. I want you to recall something. Well, we have another equation we've already seen, that a velocity is equal to an initial velocity plus an acceleration times the time. And the reason we want to do this, we have an equation here for the displacement, right? Maybe I should complete my equation. But we can go further and get an equation using acceleration instead of say average velocity or delta v. Look, there's no a in this equation. There's no acceleration term. We'd like to have one. We would like to know displacement or final position in terms of time and acceleration. That's going to be important. So what we're going to do is we're going to take this guy and substitute into that velocity. So here's how this is going to work. VOT plus 1/2. Now instead of V, I'm going to write VO plus AT. And then I have to subtract VO. So here's the substitution that I did. And then that chunk right there gets multiplied by time. Now obviously something's going to happen here. VOT plus 1/2. That 1/2 doesn't go away. We have a VO minus VO. That goes away. That's kind of cool. We have an AT times a T. We end up with AT squared. We can now find how far something has traveled. How far? We can find the displacement of something. Or if you like to term it this way, we can find its final position. If we know the initial velocity, if we know the rate of acceleration, and if we know the time of travel. So this is one of the big five equations. And this is sometimes also written, so or, you'll see this delta x expanded. So final position equals initial position plus initial velocity times time plus the 1/2 AT squared. Now, if you're dealing with positions, you're looking at a position time graph quite often. And what you'll notice, a position time graph where something is accelerating is curvy, right? If so position x versus t. And if the object is speeding up and the acceleration is positive here, then we get this curve open upward, and it would be the opposite if it were slowing down. Then somehow, so in some way, the curve would be open downward. So it might be open downward like this. There's several possibilities, right? But this green curve would be a positive acceleration, and this blue or bluish purplish curve would be a negative acceleration. Okay, so I'm going to put a box around this one also, but it really is the same equation, just two different forms of it. So that is the fourth equation of the big five equations we look at. Now, let's keep going. We are almost there. It would be nice if we could deal with this stuff in some ways where we don't know the time. Because check this out. So far, what do we have? We have an equation with time in it. We have, well, that's just average velocity, but we have a position equation with time in it, very time dependent. We have position equation with time in it, very time dependent. What if we don't know the time? We'd like to deal with velocity and acceleration without knowing the time once in a while. So, from this guy, I'm going to rearrange that solve for t. And this is going to allow us to make a substitution into another equation. Did I do that right? Solve for t, subtract VO. Yeah, okay. And that's going to get substituted into, for starters, the average velocity equation, more or less. VO plus V times t. So we're going to put this business in there. Here we go. And now I write V minus VO divided by A. Okay. Rearranging and distributing and foiling it out and whatever else you want to do. All that wonderful math, right? You end up with, try that again. The standard way of looking at this equation actually has this final velocity right out front. And so final velocity squared equals initial velocity squared plus 2 times acceleration times your displacement or your change in position. I'm going to caution you, this is the final equation here. I'm going to caution you though. Please, 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 it is so easy to lose track of those two exponents or even just one of them. And if you do, you end up with the wrong answer. You guys recognize that. So to recap, we have the big five equations of kinematics. I can call it the big five. I don't know who else does. I don't care who else does. Remember, kinematics is the study of motion without dealing with why the motion is taking place. Okay, so here we go. What are these big five? We have an equation for final velocity, if we know initial velocity and rate of acceleration. So this is final velocity at any moment in time. We have an equation for average velocity, and this is really simple. A little part of me is surprised that this is listed as a very important equation. We have an equation for either consider it final position or a change in position that deals with average velocity. There's your average velocity, but you multiply by time. We have another equation for change in position. If you know the initial velocity and the rate of acceleration. And we have one final equation that relates initial and final velocities to acceleration and your displacement. And so time is not a term in this equation. And that can be very handy at some times. All right. That is where these equations of kinematics come from. And you're reading about it in your textbook also. There's a lot of depth there. There's a lot of examples there. Please get into that and get as much out of it as you can. Thank you for watching. I'll catch you next time.